Hey, time to do some calculus homework. Let's see what we got here. Section 2, 3, 7 to 23 odds, 43 to 57 odds. There's a lot of problems. Man, it's going to take us a while. Well, let's see how it goes. Number 7. We are finding limits at infinity, thinking about end behavior, stuff like that. So I got the limit as x approaches positive infinity of this expression, which I'm noticing right off the bat, it's not even like a rational expression. There's no denominator. It's just this. So highest power rules that as we go to infinity, when we're going off to infinity, the highest power is going to dominate. So these things fade off into sadness and despair and insignificance, and this is what matters. So it's the -3 here. So that's going to approach negative infinity. And you could say does not exist. You can say that if you want. That's certainly true. This limit does not exist. But if we can be a little bit more specific, if it's true that it's just going to negative infinity or positive infinity, we can say that, and it's a little bit more information. All right. Number 9, same thing, or similar thing, I guess. Limit as x approaches positive infinity of the square root of x. That's the same as x to the 1/2. That's the highest power is x to the 1/2. That's the only thing going on. So that dominates. And the coefficient of this is just like a 1, positive 1. So there we go, off to positive infinity. Number 11. Oh, let's check what the book says. The book say, I'm looking at the wrong thing here. Let's see. 7. Yeah, they're doing the negative and positive infinity thing. So instead of just saying does not exist. So we'll do that too. All right, number 11, we got the limit as x approaches positive infinity, 3x plus 1 over 2x minus 5. All right, let's look at the powers. I got an x to the first power on the top is my highest power. X to the first on the bottom is also my highest power on the bottom. So it's a tie, which means the ratio of the coefficients of those. That's what's going on. Please excuse that announcement there. Number 13, I got the limit as y approaches negative infinity, 3 over y plus 4. The highest power of y is on the bottom. It's this. So if the highest power is on the bottom, then you are going to go to 0. And I mean, that's a good little rule, I guess, to know, but we should be able to think about what's actually happening there and convince ourselves why that is the case. If the bottom's going to get bigger and bigger and bigger, and the top is just going to be 3 or any other power that's not as big as what's on the bottom, that is going to drive that fraction closer and closer to 0. All right, number 15, limit as x approaches negative infinity, x minus 2, there's x to the first power on the top is my highest power. Oh, I got an x squared on the bottom. That is going to get driven down to 0 because the highest power is on the bottom. Number 17, the limit as x approaches positive infinity. The cube root, everything's under the cube root sign. 2 plus 3x minus 5x squared. 1 plus 8x squared. So the highest power, you could look at these and say, oh, it's x squared. It's not really x squared. It's really like x to the 2/3 because of this cube root out here. Now, it doesn't really matter for comparing the powers because they're both the same. They're both underneath that cube root sign. But I would encourage you to think about those as being really 2/3 powers because of this. So ratio of the coefficients, so that's equal to -5/8, but those coefficients are also under the cube root sign. So It's the cube root of negative 5/8. And if you're like, oh, nope, there's negative sign under this root sign. But this is an odd root, so you can take odd roots of negative numbers and still land inside the real numbers. You don't have to worry about i's and stuff like that. Because if you didn't, here's a little calculus joke for you. There's no I in calculus. See? There's no I in there. No, that's true. Of course, you can do complex analysis, which is like calculus plus complex numbers. You do this in college if you're a math major. Calculus plus complex numbers. I think some other people might have to do. If you do electrical engineering, I bet you have to do complex analysis too. It's really fun. It's calculus with complex numbers, and then that class is called complex analysis. And there it is. There is an I, complex analysis. So there you go. Okay. Now the limit as x approaches negative infinity. Oh, here we go. So this is why it's important to respect those root signs and root symbols and what's under them. So here, what's the highest power on the top? You know, say, oh, it's a 2, but it's not really because it's under the square root sign. So the highest power on the top is really x squared, right? And that means, and the highest power on the bottom is also a 1. So let's see, on the top, my coefficient is the square root of 5, and on the bottom, my coefficient is a 1. But because I'm going to negative infinity, this is a little bit tricky here. We have to be careful. That negative infinity is getting squared here, so it's going to be positive, landing under that square root sign. And then on the bottom, as I go to negative infinity, it's going to remain negative. So that positive on the top, negative on the bottom is going to get me negative square root of 5. It's going to be my ratio of coefficients. So that's a little tricky there. Number 21, cruising right along, limit as y, can you still see there? Oop, almost lost you. Y approaches negative infinity, 2 minus y over the square root of 7 plus 6y squared. Okay, so if you didn't get this one right, then pause for a second and reconsider what you did for 21 in light of number 19. Pause. Did you pause and go back and look at it? Give you another chance to do the right thing. Okay, so it looks like, again, because I've got the square root on the bottom, the highest power on the bottom, although it looks like a 2, it's really y to the first because it's under a square root sign. So on the bottom, my coefficient is square root of 6, and on the top, my coefficient is, it looks like I would have a negative 1 there, but because I'm going to negative infinity, those two negatives are going to cancel out. So it looks just like a negative over the square root of 6, negative 1 over square root of 6, but just like in 19, that negative sign is going to matter here, but not matter here because it's getting squared. All right. Flip that around, save some paper. Where are we at? 23. So same or similar kind of game here. I got the limit as x approaches negative infinity, square root of 3x to the 4th plus x, and on the bottom x squared minus 8. So it's always good practice when you're watching these solution videos to do it actively, not passively. You can just watch the show and watch the hand of the man doing the math. But it's much better for you in the long run and the short run and the intermediate runs too, I think, to pause the video a lot. And you don't have to watch the whole thing also. If there's a stretch of problems, you already checked them in the back of the book, you're good. You don't need to watch that part of the video. You can if you want, but probably you're good. So lots of pausing and engaging, getting out your pencil and working through stuff. Anyway, this is similar to those last ones, but I've got this on the top here. This is really like x squared because it's under the square root sign. The square root of x to the fourth is x squared. And so the coefficient's x that is the square root of 3. And here on the bottom I have the tie, another x squared. So I've got the square root of 3 over 1. So it's just square root of 3. And notice here, even though that I was going to negative infinity, like in numbers 19 and 21, it didn't matter this time because x squared, x to the fourth, negative sign is being raised to even powers. So bye-bye to that. Number 25, limit as x approaches positive infinity, 7 minus 6, x to the fifth, plus 3. Hey, that's easy. I mean, got to think about what's going on here, but I got highest power on the top, so that's gone. Negative sign, going to make it go to negative infinity. And that's all there is to that. 27, we're going to, oops, it's a t. I jumped the gun there. Going to positive infinity, 6 minus t cubed over 7t cubed plus 3. And going to positive infinity, so let's see. Where's the biggest exponent? It's a tie, so it's the ratio of the coefficients. Going to positive infinity, so I don't need to worry about any sign business. So there you go. I'm going to take a quick look at the answer, the solution key here, just to make sure I didn't give you any bad information. It looks like we are all good. That wasn't bad. First bit of that homework. Didn't take us that long. Checking. 13, 15, 0, 0. You already checked your answers, of course. So, oh, they simplified 17 and, you know, flexing their skills. But we don't care what answers look like in terms of whether they're simplified or not, as long as it's a version of the right answer, and we're good. All right, so next part, 43 to 57. What do those look like? Ooh, these are a little interesting. So limit as x approaches 0, e to the 1 over x. So I think these, I would consider these to be like composite functions for the most part. And I think the best way is to kind of pick away at them from the inside out. So here, what's going on with that? Forget about the e to the 1 over x. Let's just look at the 1 over x first. So as x goes to 0, the positive side, that is going to make this blow up to infinity. So in other words, if you just thought about, here's our little thought bubble, what's the limit as x approaches 0 from the positive side of 1 over x? Just looking at that part of it. So this gets smaller and smaller, positive, and 1 divided by something that's going to 0 is going to make that go to infinity. That's like, if you want to be visual about it, which I always like to do, whether you just picture this or whatever, it's like you're on the 1 over x graph and you're approaching 0 from the positive side, riding along this, and that's going to climb up toward that asymptote there, and go up to positive infinity. So what's e to the positive infinity? Well, that's positive infinity. All right, 45, we've got the limit as x approaches 0 from the positive side, e to the cosecant of x. Well, what is cosecant of x? So same kind of idea, just going to focus on this first. You know, as long as I've been teaching math, this is a horrible thing for me to tell you. I don't know what the cosecant function looks like, but I know that it's related to the sine function. So if I do need to know, I can recreate on paper or in my mind what this looks like by just imagining the sine function and then doing 1 over that, because cosecant is equal to 1 over sine x. So what if you took all the values of this sine function and flipped them upside down? Well, if you flip, this is where sine is equal to 1. If you flip 1 over, you still get 1. But if you flip 0 over, boom, you're going to go to infinita. So it looks like this, your cosecant function. When you flip over these numbers that are smaller than 1, they turn into numbers that are bigger than 1. When you flip 0 over, you get infinity. So what's happening as we approach 0 from the positive side with the cosecant function? Oh, that's also going to positive infinity. If this is going to positive infinity, then e to the positive infinity is positive infinity. So that's not so bad. Let's see, that's 40 and 47. We've got the limit as x approaches negative infinity, 1 minus e to the x over 1 minus 1 plus e to the x. All right, so let's just look at the e to the x. What happens to e to the x as x approaches negative infinity? Well, that's the same as the limit as x approaches positive infinity of 1 over e to the x. Think about what you know about exponents and negatives and stuff like that. This is going to be like e to the negative big number, but negative exponents just mean flip the thing over. So I think it might be easier to think about if we realize it's the same as this. All right, now e to the infinity, well, we have been thinking about that in 43 and 45. That's just going to blow up to infinity. 1 over infinity, that's going to go to 0, 1 over something that's getting huge. So this is going to 0, which means so this piece here is going to 0, and this piece here is going to 0. So that means it's basically just 1 over 1 here. These two things both go off to 0, and we just are left with that. All right, 49. Hey, good thing we thought about that. All that e business here. Looks like it's going to come in handy again. So x to the infinity. I've got e to the x minus e to the negative x. E to the x minus, oops, sorry, that's a plus on the top. E to the negative x. All right. So this is going off to infinity. This is going to infinity. The e to the negative infinity, that's what we just thought about here. So this thing is going to 0, and this is going to 0. So what I'm left with is e to the x over e to the x. And although those are both going to blow up, they're the same as each other, kind of like highest power, top and bottom. I have exactly the same. So however big those get, it's still a ratio of same to same. And that means we are just going to be going to 1 again. All right, what are we on, 51? Let's see. Limit as x approaches 1 from the negative side, the natural log of 1 minus x. You know, this thing that I'd like to rant about a little bit, what's so natural about the natural log function? Log base e, come on, what the heck is that about? There's a lot of great answers to that, and if you're a fan of watching math videos on YouTube, I know some people do that, right? There's on the 3 blue, 1 brown, or whatever that channel is called. I might have the colors backwards. He does a great what's so natural about the natural log. We could talk about that sometimes. but it's actually very well named. So I think what I want to do here is, this is confusing, it's a lot to think about. Maybe I just want to think about what's happening to the inside of this. So what's happening as x approaches 1 from below 1? What's going on with this? Okay, so I'm plugging in numbers that are close to 1. So this is approaching 0, but is it approaching 0 from positive or negative? So if I'm plugging in numbers that are just a little bit smaller than 1, this is going to approach 0 from the positive side. It's going to be approaching 0 from the positive side, as I'm plugging in numbers like 0.9, 0.99, 0.999, and so on and so on. So this is going to get smaller and smaller towards 0, but from positive, from above. Okay, so this thing here is really the same as, what's the limit as x approaches 0 from the positive side of natural log x? I could make that substitution, or at least think about it in that way, because that's what's happening to this, right? Okay, well, what does happen to the natural log function as you approach 0 from positive? You need to have tattooed on your brain what the natural log function looks like, and understand that it goes through the point 1, 0, that it bends downward like this, but keeps going up forever. It grows, albeit tragically slowly. It's one of the saddest stories in math, how tragically slowly the natural log function grows. It's a theme that we will come back to later in the year. All right, now what happens as we approach 0, as x approaches 0 from the positive side, and we plunge down to negative infinity. All right, so the graphs that you should be familiar with, like sine, cosine, natural log, e to the x, stuff like that. Although these problems don't look like you would have to graph things, being familiar with what they look like is very important. All right, so what's going on here? As x approaches positive infinity, this is going to approach 0, also from the positive side. So this is actually just exactly the same as the last one, once we realize that that's also going to go to negative infinity. 55. Let's see. I have, oh, this is a good one. This one, I bet you didn't get this one right the first time. There's different things that students often think about this one. There's the, okay, x, same power, highest power, top and bottom, so it must be 2/3, right? I bet you did that first, didn't you? And then you looked in the back and you're like, oh, that's not right. So it's not really exactly like the highest power, top and bottom, because these things are inside natural log. So it's a little tricky understanding really deeply, profoundly, what is going on here. But the natural log function, of course, that's just a log function, and we know rules for manipulating logarithmic functions. And one of those rules says that if you have the natural log or any other log of a product, that's the same as this. Okay, so that means that the natural log of 2x is the same as the natural log of 2 plus the natural log of x. And likewise, natural log of 3x is natural log 3 plus natural log x. Now, as x goes to infinity, the highest power of x, well, it's not exactly a power of x, but you've got these natural log of x's happening on the top and the bottom, and although it grows very slowly, it does grow forever. So these little numbers here, those just fade off into nothingness because they're just constants. So what you really have is just natural log x over natural log x, and that's same over same. So that's just 1. You could think of Let's see, are there any other problems like that? Not quite. I hate to get distracted when we only have one problem. Oh, no, this 57 is like what I'm thinking. Just kidding, it just wasn't immediately apparent to me, but it is. All right, so logarithm rules again. You might have played around with this a little bit before you realized it was a logarithm rule deal, but it is. So let's see, this is a subtraction here, so that can be rewritten as the natural log of a quotient, because that's how that rule works. Mr. Hardin's a big fan of the logarithm rules and proving them and everything, which is a great thing to do. So I'm sure you did that at some point. All right, so what's up here? Well, I've got x squared minus 1. So this we could look at highest power top and bottom and say highest power is on the top. So this on the inside is going to go to infinity, and that means the natural log of infinity, although it grows tragically slowly, it is going to blow up like that. And yeah, that's good. What I was actually thinking about, I'm just going to throw one more problem at you that I'm going to make up here real quick. If you had a situation that was like the natural log of, let's say, how about 4x squared over the natural log of x. So you might look at that, and this would be a limit as x approaches infinity. You might look at that and say, oh, the highest power is here, so that's got to go to infinity. But it would not go to infinity, and here, again, you have to think about logarithm rules, although it's a different log rule. This here is the same as 2x squared. And if you remember this logarithm rule, that the log of some number to some power p, that you can move that power out to the front. Probably prove that too. Probably so n is probably a poor choice if I'm using natural log. Let's say it's a, so number a to the p power, and you can move the power out to the front. This is a logarithm rule that we're going to use that here and there. It comes up. So that means here, if this is the same as 2x squared, then I can move the 2 out to the front. That's the same as 2 times the natural log of 2x over natural log x. And that's the same as the limit as x approaches infinity. Here, that's a product, so that's 2 times the natural log of 2 plus the natural log of x over the natural log of x. And then if I distribute that back through, with the limit as x approaches infinity of 2 natural log 2, which is the same as natural log 4 if you want, plus 2 natural log x over natural log x. Okay, so this is just a number, and then here I've got natural log over natural log, same over same, and the coefficients are 2 over 1, so this is actually going to go to 2. So that's interesting. It looked like there was a higher power here, so it's just going to blow up on top, but that is not the way that the logarithms work. So there you go. That would have been a good problem if I had written this book. I probably would have thrown that in there. All right. See you later.